here is the generalized Darcy's law. And the generalization is to account for anisotropy. So instead of a scalar value for permeability, we are going in there with a second order tensor, which is a 3 by 3 matrix. And here you have gradient of flow potential, which will give you a vector. It's the gradient with respect to the x, y, and z directions, respectively. And so you will get a vector for your flow rate in the x, y, and z directions, respectively. So only area and viscosity are scalar values. And here I've assumed you're working with a consistent set of units, like using the SI unit. But if you were to use the field unit, then you will need a constant conversion factor here. So the conversion factor will be a constant depending on what unit you're using, if the unit is not consistent. So this is what your flow potential is pressure plus rho g h, basically. But this is gradient of, it's the gradient of the z with respect to those three directions, x, y, and z. So essentially, grad z looks like this, except you're looking at z. So for the first component is going to be the z, the x. For the second component, the z, the y. And the third component is the z, which will be 1 if you're looking at a system, a reservoir, that is perfectly horizontal. So if the reservoir is perfectly horizontal, then you know that if you're looking at these two grid blocks, for instance, this one and this one, because the grid block is the reservoir is completely horizontal, then the z, the x, right? This first component will be what? It will be z2. This is grid block 2, this is grid block 1. z2 minus z1, right? Divided by x1 minus x2. And then what's the difference between z2 and z1 if it's completely horizontal? The z values for both grids are identical, right? So this difference will be 0. And then the contribution of the z, the x, will be 0. So this will be 0. I'm going to write it in a more compact form. So this goes here, and the last one goes here. So same deal for the y, right? z2 minus z1 over change in y, which will be 0. Well, this other one is the z. So z2 minus z1 divided by z2 minus z1. The numerator and denominator are the same, right? So it evaluates to 1. So that's what you have when the grids are perfectly horizontal. But in reality, most of the time, your grid dips. So if you have this type of grid that is dipping, then you can see that z2 minus z1 is not going to be 0, right? The z value here is different from the z value here. And that difference will show up in this term and this term and this term. It will never be really 0, 0, 1. You will have fractional numbers as all three entries. And so I ask you to substitute the definition for potential gradient into this equation, right? And then write out what the new equation will be. And then tell me under what condition the equation will reduce to this form where you just have pressures, right, in the first two entries, and in the last entry you have rho minus rho g. Let's talk about heterogeneity versus anisotropy. They are two different things, right? Heterogeneity refers to the fact that the property, the value of, say, permeability in this position in a reservoir could be very different from the value of the property, in this case permeability, in a different location. So that is heterogeneity. The properties are different at different points in the reservoir. But anisotropy deals with the direction, right? The value of the property in this direction could be different from the value of the property in this direction. That is anisotropy. And so I show different images here to illustrate different combinations of both. So in this case, the lengths of these vectors are indicative of their magnitude. So kx is approximately equal to kz, right? So that is isotropy. And then the lengths of these two are pretty much similar to the lengths of these two. So we're assuming they are the same, and this will be homogeneous. So it's both homogeneous, right, and isotropic. But here, is the length of this the same as this length? No, so that is anisotropy, right? And then the lengths of these two, let's pick the short one first. It's close enough to the length here, right? And then the length of this is close enough to this length. So the property at different points is about the same. It's just the property in different directions that are different. So it is homogeneous, right? The magnitudes of these are close enough to the magnitudes of this, but anisotropic because kx is not equal to ky, basically. And then we come here. The length of this is approximately the same length as this. The length of this is approximately the same length as this, so it is isotropic, right? The magnitudes are pretty much the same in the two directions. Kx equals ky equals kz. But the length of these two arrows is much longer than these, right? So the value or the property is changing at different points in the reservoir. So it is heterogeneous. It's not homogeneous. And here, the length in one direction is more than this direction, so it is anisotropic, all right? And then the lengths of these are also much longer than these, so the property is varying from one point to the other, so it is heterogeneous. And all of those are written here. So I give you a simple Darcy's law equation. This is standard reservoir engineering. No trick questions there. And I want you to walk through this and get just a quick reminder of how the equation works out. I point out that permeability is typically related to porosity. There are several different models that can be used. I'm just showing two out of them. The Kalman-Kozeny model, which is popular, and then you have the exponential model, and it basically just relates permeability to porosity in both cases. And both equation 1 and equation 2 are fitted through these data points, and it turns out it appears the exponential model, which is equation 2, more adequately fits these data sets from a specific sand, or I should say for a specific reservoir. So the best model could vary depending on the actual source of the data.